I got a reputation among the students as always asking what they consider the ecological validity question, which was how representative are those stimuli compared to the world that we're asking these people to perform in? And the answer was sometimes very unrepresentative.
You know, I think that language of control theory allows us to look at phenomena as they exist in the world in ways that the causal model simply doesn't work.
Welcome back to HFIG Talks. I'm Audrey Ben-Mergi, HFIG's current undergraduate representative and one of the communications directors. And co-hosting with me today is Professor Mark Chisnell, HFIG's faculty advisor. Today's episode is featuring Dr. John Flach and Dr. Alex Kirlik. Dr. John Flach is a senior cognitive systems engineer at Mile 2 in Ohio, where he works to design and build software solutions to help businesses and other enterprises manage complex work. Before that, Dr. Flach was involved in graduate and undergraduate education in applied cognitive psychology at the University of Illinois at Urbana-Champaign, and most recently at Wright State University, where he was a full professor and the chair of the psychology department. Dr. Flach's research interests are in applied cognitive psychology and cognitive systems engineering. His work has spanned a wide range of application domains, including aviation, military command and control, and healthcare. Dr. Alex Kirlik is currently a professor of computer science, electrical and computer engineering, and a member of the Beckman Institute for Advanced Science and Technology at the University of Illinois at Urbana-Champaign, where he joined in 2001, serving for 5 years as head of the Human Factors Division in the Institute of Aviation. His research interests include modeling and supporting the design of human technology systems in professional contexts, interactive visual analytics, judgment and decision-making, ecological psychology, and the ethical implications of digital technologies. With their extensive experience in human factors, Dr. Flach and Dr. Kirlik have seen evolutions of the field, and today we spoke about those and especially the changes in the fields of control theory and ecological psychology, which they have both specialized in. Thank you both for joining us here today. I just wanted to start by diving into the past a little bit with the fact that you all know each other. Can you tell us a bit about that story?
Well, John and I actually share at least a co-advisor. I'm not sure the technicalities of who has what title back in graduate school, but Richard Jagosinski, a professor of psychology at Ohio State with interest in perception, control, and decision-making, really was an important player for both me and John. Maybe Mark Chisnell also may have taken some of Rich's.
I did take his courses, and I remember when he had that helicopter set up. I remember he had this big helicopter world that he did with NASA, and right. I remember them working on that because it's right outside my office.
Yeah, yeah. He had. So I'll let John fill in his relationship with Rich, on his own. But for me, what was happening is I was working on my PhD in industrial and systems engineering with an interest in human machine systems, human factors. And I took a course with a professor in systems engineering named Al Miller. Mark and I shared that experience. And it was a challenging course. And I guess I did well enough to get invited down to the lab one day where he and Rich were kind of co-advising a research project funded by NASA. And they made the traditional graduate student promises, we'll give you a chair and a desk, nothing else, no money. But if you're still here in a few months and our senior graduate students think you're making a contribution and we do, then maybe we could talk at RA or something. And so then that was really opening the door to me having the wonderful experience of being co-advised by Rich Jagosinski in psychology. Rich had a bachelor's degree from Princeton in electrical engineering, and Al Miller in industrial and systems engineering. And Al Miller was a student of Tom Sheridan's at MIT. And Dick Pugh, of course, was someone who played a formative role in Rich's career. So I'm kind of like one of the maybe many grand students or grandnephews of Dick Pugh and Tom Sheridan, two leading lights in the human factors discipline. I hope that when this is all said and done, I can make 5% of the contribution that they made. So John, why don't you jump in here and give us a little background around that time?
So you're leaving out one of the most important people in your heritage. Dick Pugh was, of course, Rich's advisor, but Paul Fitz was Dick Pugh's advisor.
Of course.
Yeah, and so Alex was in industrial systems engineering. I was in psychology, and actually similar to his story, I got accepted to Ohio State, but without any funding. And but my wife got a job near there, and so we were going to go to Ohio State. But I got a call in the middle of the summer before I started in the fall from Rich that his graduate student Al who was Dwight Miller, not Al Miller, Dwight Miller, had taken an internship with Honeywell, and he had an opening in his lab, and he needed somebody to come up and work on this project. And so I leapt at the chance to get my graduate school funded. But I didn't know what the work was until I got there. And the first day I got there, I'm a psychology student coming here to study psychology, thinking I'm going to study attention. And he sits me in front of an analog computer. And he says, well, of course, you put two integrators back to back in a circuit, you get a sine wave out, right? And I'm like, whoa. So I go home and tell my wife, well, I'm in big trouble. And at that point, again, my undergraduate, I started in biology, chemistry, and then went to psychology, but I didn't have a lot of math or any engineering at that point. And the project was modeling tracking performance, comparing visual and tactile displays using frequency domain analysis. So I had to learn how to do Fourier analysis, and so I ended up during 6 years of graduate student, taking a lot of engineering courses, sat in on Al Miller's course. I think we used Leuenberger for that course that I took with Al. Most of the time didn't understand what was going on in most of the engineering courses, but I listened and I must have absorbed something. Fortunately, I didn't have to take the tests in those courses. But what I remember about Alex, and when we were students, we didn't interact that much. We had to come an advisor, but I remember going over and getting you demoing your helicopter simulation. So the project that Alex was working on was, at that time, was it LHX project, and the military was asking, whether one pilot could control this thing, or did they need two pilots for this helicopter. And so, I met Alex then, but we didn't interact too much while we were in graduate students. But then what I remember most distinctly about Alex, that really put you on my radar, Alex, was the chapter you wrote on that work and the map and perhaps the story you told about, as you were doing it, you became so familiar and understood the task constraints so well that you could perform better than any two-person crew.
Yeah.
And
that actually was my attraction at the end of the day to Gibson's affordances, in that I was training subjects who were naive at the task. And if you've ever had that experience where you're fairly expert at a task and you're training someone who isn't, you can't describe what you're seeing to that person very well. But it seemed like the selection of action was pretty unmediated to me, as if I was seeing the opportunities for taking action directly in the world. And that's how the theoretical part of the papers would go, in terms of using Gibson, which is a shared resource for both of us.
And if you remember in the chapter, what you did is essentially showed layers of constraints and a diagram. And once you had all the constraints laid out, again, I think it's your metaphor, the cognition was like having a marble and just rolling it down and following the path of least resistance, in a sense, in that space. And so, to me, that was actually one of the best arguments for an ecological approach, even better than what's coming from the ecological community at that time, because you actually demonstrated how understanding constraints and the problem constraints actually leads naturally to the solution And essentially the cognition was just tuning to those constraints. Once you were tuned to those constraints, the solution became almost intuitive or obvious.
Yeah, well, thank you for the compliment. That actually brings to mind some memories that are associated with trying to then sell that work to the various intellectual communities. So what I had done was essentially marry kind of Gibson's affordance theory of the selection of action as being relatively unmediated and in the spirit of ecological psychology, with a computational approach to simulating human cognition, selection of action, and performance. So what do you think happened? I was lucky enough to get an invitation to speak to a Gibsonian audience. And they said, this is irrelevant. You're modeling a person on a computer, and we don't believe in that. Cognition isn't computational. And I said, when you run a hurricane simulator, you don't all get wet. Okay, I'm just using that as a tool. And that was something I could never get across to the Gibson people. Then, of course, when I went to George Miller's session hosting Susan Shipman's cognitive science grantees at Princeton one year, and I gave the talk there. And they, of course, couldn't see the relevance of Gibson at all. That Gibson isn't that the guy who was completely wrong about everything about computational models of cognition, because he didn't believe in them. And so I was 0 for 2 on that, but managed to kind of stick to the knitting and was lucky enough to find some people who were interested in actually looking at solving some interaction problems, and was able to find a constituency for my ideas in the practical and the applied, rather than the highfalutin kind of intellectual thin air of psychological theorizing.
Yeah, and for me, one of the keys to my evolution as an ecological psychologist was when Rick Warren came. Dean Owen was talking about the philosophy behind what Gibson did, but Rick had worked out the optics, the mathematics of the optics. And my first job was at Illinois, and partially a major appointment in mechanical industrial engineering. And that's where I had to start teaching controls. And that's when I actually started learning controls, when I had to teach it. But was also appointed with the Institute of Aviation. And with a flight simulator, a visual flight simulator, that was a real nice opportunity to take the mathematics that I was learning from Rick Warren and use parameters of the optical flow, the invariance, as inputs to a control model. And we could actually, and in those days, we were just developing the technology so you could have interactive. So, I don't know if you remember, Mark, but at the Aviation Psych Lab at Ohio State, they had to build the graphics board just to allow us to kind of real-time interact with a checkerboard and fly over a checkerboard. And so when I got to Illinois, we had Silicon Graphics computers, some of the first Silicon Graphics computers, and we could actually do interactive tracking with optical and manipulate properties of the optic field. And so that were some of the first experimental tests of the idea of optic flow, and that constraints and invariance in optic flow was information for guiding locomotion. But, interesting, when I got to Illinois, I thought the mathematics was interesting. The philosophy of ecological, I still didn't quite grok or appreciate. But when I got to Illinois in the Institute of Aviation, they're flying this flight simulator, and I'm trying to map, talk to them about optic flow and the possibilities, and they just didn't get it. And in fact, I can remember being at meetings and people, no matter what it was, sometime during the meeting, someone would look my way and say, well, John, how would Gibson resonate to that? As if it was and I just got really stubborn. The more I defended it, the more I believed in it. But what they were doing is they had a flight simulator. They had they have, interactive optic displays, and they were having probably fly the flight simulator, but they were giving them a Sternberg task. And they didn't have anything, they weren't modeling the flight. That was just a secondary task. The key question was, well, did you get a slope or intercept effect on the Sternberg task? And that, you know, they literally talked about the Sternberg task as being a dipstick into the mind. And so they thought they were getting really grand insights into the piloting by knowing whether flying interacted with the slope or intercept in a Sternberg task. And that would tell them whether it was, you know, perceptual or cognitive, at least that's what they thought. So to me, that just, that, you know, they were missing a huge opportunity to take advantage of the graphics that we had in that. And for me, Gibson gave me a way to latch on to the structure and optical flow fields and talk about optical flow fields as a stimulus and really build in, which later, working with Rick Warren at Wright-Patterson Air Force, you know, we tried to frame kind of what we called active psychophysics, where we could tie the optical variables to the closed loop dynamics of piloting.
Well, I would hate to be accused kind of piling on here, but I think what you saw, perhaps, John, after having been in Illinois for 20 years now, it was less kind of strongly felt theory that would run upstream from your theory, and more kind of an experimental orientation in practice that saw perceptual richness as only a barrier to understanding. I can't tell you how many dozens of talks I've gone to the 8th floor of the psych department here on, say, visual search, which is kind of probably gotten 50 psychologists their tenure and promotion. You typically have people presented with these static patterns of T's among F's and F's among T's, and they're asked to pick them out. And I think I got a reputation among the students as always asking what they consider the ecological validity question, which is, I think, ill-posed, but at least they had a feeling for it, which was how representative are those stimuli compared to the world that we're asking these people to perform in? And the answer was sometimes very unrepresentative.
To me, that's the legacy of Rich Jagosinski and Al Miller, is they taught me, and I think you as well, to see the world in terms of circles, in terms of dynamical circles, closed loop dynamics. And most cognitive scientists are still looking into the world in terms of arrows, that is cause effect. And it's really hard. I mean, you know, ever since the cybernetic hypothesis was introduced to psychologists, you know, psychologists draw closed loops in their models. But the first step in almost all their experimental methods is to break the loop, because they want, as an experimentalist, to control the stimuli. And when the loop is closed, that means the subject controls what they see, because their actions determine, and that's antithetical to the principle, you know, that's guided a lot of experimental research and experimental psychology, and that's a principle, is that you as experimentalists have to have complete control over the stimulus in order to draw any useful inferences. And, you know, again, you'll see closed loops in all the diagrams and all the models in cognitive science, but in their logic, in their theory, in their methodologies, I don't think they really respect the dynamics that I think are essential to adapting to the world and to success in the world.
Clearly, another way of looking at closed loops for people maybe who might be reading this who aren't familiar with control theory, and I guess I'd like to ask that you unpack that a little bit. But my anecdote along those lines is that one could look at a closed loop as essentially saying the arrows point in both directions at the same time. I think Dewey was going this way after in his reflex arc paper and notion more than 100 years ago now. And I was somewhat recent. I had recently read Dewey, and I was writing up a chapter for a very cognitive sciencey book, edited an edited volume in the area of cognitive modeling. And I wrote in the chapter something about the arbitrariness of how you cut, where you cut, and what causal effects you're looking for. And clearly what we typically do is cut it in such a way, psychologists do, so the environment is the independent variable and behavior is the dependent variable. And I said, but that's completely arbitrary, as Dewey wrote, because our actions structure our perceptions just as regularly, if not more, than our perceptions structure our actions. Well, the editor of the book got back to me and says, I can't understand what you just said all. And I said, well, it's an easy notion, right? To what degree is the perception you're currently having at your desk determining what actions you'll take? Well, maybe the playing field, but not which one, right? On the other hand, now move your head around your desk. To what degree are the actions that you're taking as you move your head around the desk structuring the view that you see? Almost perfectly. If anything, there's more of a lawful relationship there in terms of looking at the arrow pointing exactly 180 degrees out of phase with the standard experimental paradigm. And of course, then giving over control of the independent variable to the subject, you know, is an issue that's anathema to any experimentalist. So in a way, what maybe we were selling in terms of closed loops, if we were wiser, you know, we might have picked the easier kind of battle. Yeah. But I think it would be valuable. I know I'd like to hear it. You know, what benefit you think looking at things from control theory has brought to your career, or your understanding of these problems.
Well, so just to summarize what you said, I mean, Gibson said it very simply: is the feet are critical, important part of the visual system. And it's the fact that we can move our eyes around that allows us to engage with the world. Well, you know, I mean, I don't have a control condition. So all I know is that seeing the world through closed loops has opened lots of doors for me and closed many doors. So it's allowed me to kind of move across into engineering, but also to look at organizational dynamics and things. And, you know, the other thing that happened kind of serendipitously for me at Illinois is Peter Kugler came there the year after I got there, and Peter was really looking at chaos and introduced to nonlinear dynamics and chaos and self-organization. And so, you know, I think that language of control theory allows us to look at phenomena as they exist in the world in ways that the causal model simply doesn't work. And for me, it's allowed me to cross disciplines fairly easily, because, you know, and again, this is, if you go back to the Macy conferences, you know, when they first introduced the cybernetic model, you know, people, you know, McCulloch is saying, God, we see closed loops all over the brain. And then you have, what's her name, Margaret Mead is saying, well, you look at cultural systems, you see closed loops all over the place. You know, closed loops are, you know, again, I can't, so either the fact that closed loops are everywhere, it either says something really important about the world, or it says something very important about who I am, that I see them everywhere. But I just see them everywhere. And again, it's opened the door. It's made it hard for me to communicate to other cognitive scientists. But it's allowed me to develop relationships with people like Jens Rasmussen and other people who see, Don Norman and other people who are the people in the design world. It's helped me move, you know, we talk about the human factors world and the computer science, but there's the other community is the design community and the UX community and stuff. And again, I think they're more in the intuitions that come from seeing the world through the lens of control theory and dynamical systems theory, I think gives us a language to go across disciplines and actually surprise people and to see things in the disciplines where we're not even the experts, but we can sometimes see things that the people who've lived in disciplines a long time see and say, oh, aha, I've never looked at the world that way. And sometimes people appreciate that. But sometimes people say, oh, you're talking, I don't understand what you guys, as Alex is saying, no, I don't understand what you're talking about in terms of his experiences.
I'll just jump in here and say it's really interesting to hear about this special interest that you both have in control theory and ecological psychology. And maybe for some of our listeners who might not be super familiar with these concepts, can we talk a little bit about how these apply specifically to human factors?
John?
So why is the human in any system? What's their primary role? And I would argue that the only reason you have a human in any system is to close the loop. The pilot closes the loop in the airplane. The nuclear power plant operator closes the loop. They close the loop at different levels. So, but at the end, it comes down to their controller. They're either a manual controller or a supervisor. But in both cases, they're actually closing the loop. And, in terms of the evolution of human factors and kind of, and I think this might be of particular interest to people trained at Toronto, but the idea of cognitive systems engineering, a lot of the intuitions of cognitive systems engineering came from people like Jens Rasmussen, who understood control systems. And it wasn't about his understanding of humans, but what he understood is design control systems have boundaries. And the design control systems in nuclear power plants are going to run into situations that weren't anticipated by the people who designed those control systems. And he realized when that system hits up against those boundaries, there's only one solution, and that's that smart humans intervene. And so that meant that the human operator couldn't just follow procedures, because if we could proceduralize it, then we can build an automatic control system around it. And so to me, that was a real shift. Up until then, human factors was all about, can you see the displays? Can you manipulate the controls? What's the relationship between the displays and the controls? But what Rasmussen said is, well, if we know the relationship between the sensors and the controls, then we just automate it. But what the humans need to do is when those solutions break down, and the humans are there to solve problems, and they have to be problem solvers, and that they have to diagnose and do the fault diagnosis and stuff. And being a good fault diagnosis in those systems means you got to understand the dynamics of closed loop systems. And so he began to, I think for me, cognitive system engineering is a real shift from looking at the human as a manual controller in these systems, where it's all about perception and action, to the human as a supervisor and a problem solver in these systems. And that's where the cognitive science becomes very important. Decision-making and problem solving becomes critical. And so, most of my career is about understanding humans as problem solvers. And the thing that I most like about the work of human factors is an excuse to follow experts into their domains and to watch how someone who's well tuned to a domain, who has expertise in a domain, can do things that exceed the capacities that all the information processing models said were limitations on human performance. So, that experts do superhuman things, but to understand that, and this goes back to Alex's paper, why are they seem like superhuman things, but actually it's just because these people are attuned to the constraints. And so what looks like a superhuman intelligence and problem solving is actually just a barbel following the gradients that it has attuned to over 10 years of experience.
My my own interest in these issues is, I think, in a certain sense, less concrete than John's. I mean, John actually uses the mathematics to model these systems and the humans in these systems, and it's gotten great insight about things like displays and so forth from that type of modeling. The kind of modeling that I have done, nevertheless, though, has been informed very much by control theory in terms of the general picture of being away from the human being something that's an input-output transducer and toward a adaptive system that does whatever it needs to do given the task demands that are placed on it. Now, there's limits to that, okay? We do get breakdowns in systems, we get human errors, but the search is for ways that people adapt to the environment and changes to the environment. That's very much in the spirit of control theory. In the paper that John cites, if memory serves me correct, that's in the Ecology of Human Machine Systems volume that you edited with a number of colleagues for Earlbaum. I believe I may have cited some of the early manual control theories as saying the search for the human transfer function, this mapping from stimulus to response in control behavior will be a fruitless quest because the person is always adapting to the environment. So there is no one-one mapping. They're simply closing a loop in such a way that the overall closed loop has a certain property, say of stability, but you don't know prior to knowing what the plant dynamics are, what the actual demands the human will be faced with. So that general picture I've taken from John and my education in control theory has very much prompted me to think of getting away from a search for the human transfer function, something like the or God's ultimate Actar model of the mind, to something that's much more adaptive and therefore not well defined prior to knowing more about the environment that is being performed in.
Yeah, and when we talk about ecological approaches, I mean, the first name that usually comes up is James Gibson, but actually the much stronger influence on my view of the world is Eleanor Gibson. And Eleanor Gibson was talking about attunement and the learning process, perceptual learning process. And this is, again, the process that I think Alex experienced in his helicopter simulation, and his diagrams kind of represent the asymptote of the attunement to that task, and represents that once you tune to the constraints over time, the cognition is specified by the constraints, not by the brain. And in terms of control theory, I mean, for me, the key was understanding McGruer's crossover model. And the basic model is of the human machine plant, and it has that form because that's what's required to make the system stable. And so, and if you shift the plant dynamics one direction, the human has to shift their dynamics in a complementary direction to meet the constraints of stability. But the form of the solution, the transfer function of the human is not dictated by the brain of the human. It's dictated by the requirements of stability for the loop. And those requirements are different depending upon the plant dynamics. And so with practice, it's amazing that humans can actually tune their transfer function to a wide range of different dynamics in the world. And again, that's the thing. I mean, that's the thing. I guess, when I started out, I never started out to be a professor. I wanted to be an athlete. I've always admired people anybody who's really skilled in what they do. And I always wanted to know what the secret to that success was. And I went to psychology because I thought it was something in people's heads. but really it's, I discovered the answer in Eleanor Gibson and her description of perceptual learning, and this idea that you're tuning to constraints in a domain. And that's what differentiates, when it's reflected in simple constructs like chunking. I think chunking is just one way of articulating what attunement means. That is that when the grandmaster is able to, chunking means that he can see higher order patterns on the board. But the chunks are not, as cognitive psychologists tends to think about them, as things in the head. They're actually constraints of the game that determine weakness or strength of positions and things. These are patterns across the pieces that the grandmasters learn to resonate to or to pick up. But the chunks are not kind of an arbitrary kind of trick for grouping information in memory. They're actually, I think, attunement to patterns that have functional significance in terms of how well you play the game.
Hey, to get back to Audrey's question, so she asked for some practical advice, I think, for a student starting off in this area, say, in the medical world. And as I listened to John, given that I've had a long-term experience in terms of knowing John and his theoretical orientation, I can cash out what he's telling me in terms of practical advice. That it may be difficult for a student to do that. One thing you might be hearing is that if you ask people with an ecological mindset on human factors, how they would go about looking at a particular design problem, they're not going to run to a dashboard, or they're not going to run to some particular platform or some programming language or even some modeling language or certain type of deep learning technique or any type of technologically oriented solution. The first thing they're going to do is study the chessboard for the game that you want them to play. They want to know more about what are the constraints the behavior has to reflect and represent. What are the reward systems or the value functions here? What does it mean to do well? A performer should be able to see how well they are doing. Many of our devices don't even allow us to do that. I know my remote control for my TV doesn't do that. So what I think, in a certain sense, what a control theoretic perspective or ecological perspective on human factors gives you is an appreciation for first taking a very deep dive into the domain and really coming to, you'll never get to a level where you understand it as well as your domain experts or your practitioners, but to start there and only afterwards start to entertain various technological possibilities you have for helping people meet the constraints of the domain. Does that sound fair, John, at a high level?
Yeah, that's fair. And in terms of the training, you're rarely going to use the mathematics of control theory once you get to complex systems, to a certain level of complexity, because it just becomes intractable. But I continue to believe that a good basic course in controls with simple control systems is a foundation for intuitions that are going to carry you into domains of all complexities. And partly is to just understand the issue of stability as an emergent property, and to realize that when you're talking about loop dynamics, you can't trace a signal causal around that the stability is a constraint on the whole. And you need to understand that whole, and you need to understand the plant, which is kind of, in a sense, the analog to the chess game, in order to know what the control system has to do. And one of the more important things that I've been thinking a lot about lately, that you kind of triggered just now, is you talked about the value systems. And I think this is something that not only do control engineers miss, but cognitive scientists miss it all the time, is the importance of values. So when you're talking about that solution to a particular plan, optimal solution or the best solution, you have to specify a cost functional. Okay, and this is a values. What's important? What's the speed, accuracy trade-off? What's the right balance? What's the appropriate balance? There's a value system. And the reason people miss it is the cost functional is not a box in the control diagram. It's external. And in tuning that system, for building an actual control system, that cost functional is in the head of the controls engineer, not in the plant itself. And he tunes his gains appropriately given his value functions. But for biological systems, they don't have an engineer with a value system to tune their gains. So they have to discover what the appropriate values, what the appropriate cost functional is. And part of expertise is knowing, where the opportunities are, what the payoffs are, but what's the right balance, the trade-offs between risks and opportunities, and what's a reasonable risk versus a foolish risk. And those all come out of the value systems, but there's no box in your control diagram, typically, that represents that cost functional.
Can I jump in with a question? Sorry, John, you set me off here. I'm still remembering that course that Dean Owen taught on direct perception. I'm not sure if this paper was in that course, but I always remember the title, Ask Not What's Inside Your Head, but What Your Head is Inside Of. And what I'm wondering is it really that, or is it ask what's your head's inside of, and then ask what's inside your head? So get the external constraints out first, and then look at the internal value functions or whatever it is you're dealing with. I wonder if you could comment, either of you, on that.
So that's something that comes up over and over again, and it's also related to this idea of memory. And so, again, I think when I bring up the idea of values, you think of, well, values are something inside, internal, that you have your value system is. But that's in the moment, the values are a thing, but values are something that I think evolve over time. And one of the other, I think another mistake we make, and kind of based on a reductionistic causal, is we try to cut up time into instances. But values emerge out of events. So you learn the values from playing tennis many times over and losing, and you begin to balance, and you're tuning that cost functional. But that cost functional, what's the appropriate value system, is defined by the real consequences and experiences in the game. So it's still, even the value system is something that you don't, it's not intrinsic to you, it's intrinsic to the game. There's an appropriate value system for if you're, climbing mountains and going into, or, skiing in risky environments and stuff. There's understanding what the risks are and the consequences and the potential costs of different actions are. Those costs and risks are properties of what the head's inside of, not inside the head. But someone who spends a long time in a domain, in experience, their calibration to the risks and consequences becomes very much better tuned than someone who's a novice in that domain. And so, again, we think about values as preferences in our head, but I think those are consequences if you look at the longer time. So your values are not part of your genetics, they're part of your experience. And they emerge based on, your values as a professor depends in your, how you decide to allocate your time in terms of publication and students and stuff. Those emerge from your experiences. And so, and again, this is the challenge of closed loop systems is we want to put the cause in the head or in the world. And actually almost asking that question, Mark, you're kind of saying, okay, which is a causal factor and which is a secondary factor? Well, it's a circle. It's a circle, so they're coupled. And even the question to put it here or there misses the point of circles, I think. Okay.
I guess my feeling is as long as there's something inside the head, for those 86 billion neurons to do, I'm happy, right?
Well, they're just but that's it's a neural net, right?
Yeah.
So it's a complex neural network, and that gives it a high capacity for adaptation that Alex is talking about. But the gains in that network are not determined by your biology. The gains in that network, or that neural net, are determined by your experiences. And your experiences happen in the world, not in your head.
Yeah, I think we can agree on that.
This actually gives me an opportunity to bring up another psychologist who's one of my intellectual heroes, who people don't think of him as an ecological psychologist, but he was very much, which was Gibson's contemporary, Egon Brunswick, who's had his major influence in judgment decision-making. And there, the whole field of judgment decision-making has taken as absolutely central, unlike these other areas of cognitive science, this notion that you can't say anything without understanding the decision task, the judgment task. And they followed in the footsteps of Brunswick this way. And what you have is this thoroughly vibrant, ongoing exercise in terms of understanding the interdependencies between the cue criterion structures in the environment. That is, the information I have directly available and what do I really need to know. You know, there's the map put out of where the hurricane is, but is it going to hit me? Okay. Brunswick emphasized understanding those statistical relationships, and then seeing how a human builds a model of those to become an effective predictor of what's going to happen in an uncertain world. So for Brunswick, and my students have done some work at bringing these notions to human factors. For Brunswick, first understand what your head's inside of. Well, it's inside of this set of fallible indicators that specify what the organism really needs to know to be well adjusted, well adapted to its environment. The problem is that there's a mediated relationship between what I really need to know and the information I have at hand. So I have to understand how that's being mediated in terms of these probabilistic cue criterion relationships and the inference that I need to make in order to be successful in that world. So Brunswick would say, and people in the tradition say, if you want to understand how a person performs a judgment or decision task, first say, what is the person inside of? What is the world of cues that are available? And how do those cues bear positive, negative relations to what the person's trying to judge or make a decision about? And then ask what is inside the head by saying, to what degree is the judge in that neural net modeling those relationships? And if the models are commensurate, okay, if I weight the cues very heavily that are very well predictive of what I need to know, I will do well. On the other hand, if I'm a poor judge, I put a lot of weight on things that are not at all predictive, put no weight on things that the expert is really weighing very heavily, and I'll be a very poor judge. So unlike, say, the study of attention and memory and other things in psychology these days, we can point to the area of judgment, I think, especially, and to some degree, the theories of decision-making, as being success stories for the ecological approach to the psychology of human beings and so forth. I'm one of the few people who looks at things that way, because not too many people through their work have to solve problems to reason across them. There's nothing, no extra insight or talent or anything that we have. It's simply that when you look across dozens and dozens of settings, you're drawn to models that are workable across that range. And so we may look at things a little bit differently than a psychologist studies attention for their entire career, for example, or working memory or something like that. But very much the study of judgment, go read Dan Kahneman's book that he won a Nobel Prize for. It very much says, don't stop thinking about what's going on in the head. First, figure out what are the cues, and and what does the organism need to know, then see how well the person can come to know those cues and make those inferences.
So speaking of Kahneman, how do you feel about the heuristics and biases with Kahneman and Tversky? Does that fit into your world?
Get me started.
Well, there's some, so you'll get all kind, and if somebody wins a Nobel Prize and people come out of the woodwork trying to tell you what's wrong with it or why they knew the same thing 50 years beforehand. Listen, there's I think what is going to be sustained as a potential criticism of his approach that will have legs is due to the empirical foundation of that work. The few places where I think the book really shines, for example, Thinking Slow and Fast, which is a wonderful read, I recommend it to all people in this area, is when he starts to talk about some of the more kind of contractual work they actually did for, say, the Israeli government or Air Force in, say, selection and so on and so forth, where they actually studied experts. I think that stuff will stand up. People will always be more interested in understanding, human foibles, mistakes, screw-ups. John has his own take, I'm quite sure, with Kahneman.
Yeah, we're pushing his buttons, I think.
Yeah.
Yeah. So, I mean, the heuristics are true, but to call them biases actually makes a mockery of the whole work, I think. And it's kind of, again, there is a belief in cognitive psychology, because what they want to do is figure out what the constraints are in the head. And so when people are working well, you don't have any information on the constraints. But when the idea is that when illusions in perception and errors in decision making, those allow us to see what the limitations of the brain are. And first thing it's important to understand is that there are real limitations. So there are constraints. So there's constraints on what we can see. There's constraints on our attentional capacity, how many things we can deal with at once. And so, 7 plus or minus 2 is a reasonable heuristic about what the limits of attention is. But if you talk to Erickson or the people who work with expertise, they say even though those constraints are real, those constraints are almost never limiting factors in terms of performance. And that once you understand the tasks of constraints, that is, once you understand the patterns on the chessboard, your performance is not bounded by 7 plus or minus 2, because you can see everything you need to see in within that capacity. When you can only see, your eyes are focused in the front, so you can only see what's in front of you. But if you're an experienced driver, you know where to look to know what's happening behind you and to the side of you and to the right, and you know what frequencies to sample the information in order to pick up, even though those constraints are real. But as far as Kahneman would go, I think he's framed the talks around what's convenient for experimental and causal explanations. And he doesn't really ask about where, and they say this, but then they never act on it. They say, well, most of the time these heuristics work, but they have nothing to say about the situations in which they work. They don't spend any ink on that, very little ink. If you want to understand heuristics and the attunement, I would point you to Gigerenzer's work, and where he talks about where instead of talking about, and by the way, just in terms of tradition in computer science, if you go back to Simon and Newell, the hallmark of human intelligence for Simon and Newell was heuristic thinking. That is, it was the ability, if you could put an algorithm into a computer that would generate answers mechanically or automatically, that was not artificial intelligence. The hallmark of human intelligence was the ability to go beyond the information, to apply constraints, heuristics, tricks of the trade to do really clever things in the world. And I think Gigerenzer frames the argument much that way. And he has lots of lots of experimental demonstrations where what looks like a bias in some contexts are actually very well adapted to many natural situations. And so these heuristics are not symptoms of a broken brain, but they're just the natural things when you take rules of thumb and ask people to put them in a situation where that rule of thumb doesn't apply. And so, you know, to me, that whole collection of research is experiments looking around for a problem that humans will make it. So you got to have a problem that that has a logical solution, but a lot of people make mistakes. And if you can find that problem, then you have 10 publications out, and you can build a beautiful narrative about why people are stupid and why we need AI to replace humans in complex systems. And that's, to me, antithetical to everything in human factors and to my belief about the importance of joint cognitive system, and to the whole idea that the reason humans are in these systems is that they're better problem solvers than most of our automatic control systems. And so we want them to be the last defense against complexity.
Really interesting, optimistic perspective. As we're wrapping up, I think we've talked a lot about these changes in different areas in human factors like cognitive systems engineering, heuristics, and biases, and all these. And so I'm just curious as to what direction you see the areas of human factors evolving to in the future.
I think inevitably human factors is going to get caught up in terms of the new kind of paradigms for machine learning and new AI and big data. Like much of computer science, inevitably there will be an increasing number of wonderful positions in industry and government labs for people who build new tools and techniques using those technologies. I do hope, though, that those people who end up developing that skill set develop a commensurate skill set that acknowledges the value of going kind of with getting your hands dirty in particular domains to better understand them and to understand more than I fear that they'll understand things up to their files, you know, that it'll become a discipline that plays around with numbers like a lot of other big data fields. So we need those people that are kind of anchored in the domains to bring those people, the modelers and the AI people, back to reality. So I think that that's a wonderful development to keep abreast of the latest methodological techniques, but I hope there's still time left in the curriculum and the research schedule for people to complement what skills they learn there in modeling and AI with the importance of direct hand observation and interaction with people and other things in the work domain.
Alex probably has a better pulse on where the field is going. I'm not sure where the field's going. I'll tell you where I'm going though. And you know, most of my career is focused on individual performance. So the individual decision maker. But for the last 3 or 4 years, really over the last 10 years, my attention has shifted to organizational decision making and team processes. And, you know, I'm now of the opinion that nobody makes an individual decision in this world. Decisions are not made by people. They're made by groups of people. They're made by families. They're made by organizations. They're made by teams. And, you know, I think, to me, the big challenge is the kinds of problems that are pressing problems in the world today require collaboration across disciplines, you know, across people, and understanding the dynamics of group decision-making, team decision-making, I think is going to be essential to our future health and survival.
I want to thank both of you, Alex and John. It was great to see you again.
Thank you. It was wonderful. Thank you all very much.
Yeah, thanks.
Thank you both for sharing your experiences, stories, and insights with us. I'm sure our listeners will find this super helpful and intriguing, and hopefully we get to continue the conversation sometime in the future. And thank you everyone for listening to this episode of HFIG Talks. I hope you enjoyed and learned something new from this conversation with Dr. Flach and Dr. Kirlik. And I hope you tune in to our next episode coming soon.